So last time we talked about dispersion. That was our first intermolecular force that we looked at. So again, just to recap, dispersion, anything that has electrons, has dispersive forces. What we'll say is dispersion increases as polarizability increases. So the way I like to think about that is how well can the molecule accommodate the electron density being shifted, or maybe that symmetry being disrupted within a molecule. We talked about last time that polarizability increases as molecular mass increases, and it also depends on the molecular shape. So if you have an elongated molecule, it will be able to displace that electron density much more readily than something that is more spherical in nature. So today we're going to talk about our next intermolecular force, dipole-dipole interactions. What we want to focus on here is the key difference between dispersion and dipole-dipole interactions is now we're starting to look at polar molecules. So recall, a polar molecule is whenever the electron density within the entire molecule is not symmetric. The dipoles do not cancel each other out. There is a net dipole in the molecule. So for instance, if we were to look at HCl, okay, so for HCl, we know that chlorine is more electronegative than hydrogen. So the electron density is going to be shifted towards chlorine. With that electron density being shifted, we know that chlorine has a partial negative charge and hydrogen has a partial positive charge. Well, if you have a neighboring HCl molecule, what we'll end up seeing is, again, this molecule is going to be polar, and we would see the electron densities being shifted towards the chlorine. So we have a partial negative charge on the chlorine, a partial positive charge on the hydrogen. There's actually going to be a Coulombic attraction, so an attraction between this partial negative charge and this partial positive charge. I'm going to draw that interaction with a dashed line here. So this is going to lead to a stronger interaction, especially at a similar molecular weight compared to a dispersion reaction. And what we'll see is if something has a dipole-dipole interaction, so polar molecules interacting with other polar molecules, the liquids and the solid phases are present at a higher temperature than what you would expect based off of just dispersion forces alone. And this can be a huge network of interactions, okay? So it's not just limited to only two molecules interacting. We could have another hydrogen chloride molecule here interacting. And we could see that there might be an attractive force here, but then there could be some repulsion because both of the chlorines here would have a partial negative charge. But what we'll end up seeing is that whenever we're looking at a system made up of multiple molecules, that the attractive forces will overrule the repulsive forces. So here are some things that you really want to look at whenever you're looking at dipole-dipole interactions. The greater the difference in electronegativity, it's the stronger the Coulombic attraction. So remember the trend for electronegativity. If we were to look at a periodic table, it increases, as we would say, up and to the right. But really what we're saying is as the effective nuclear charge is increasing and the number of energy levels is decreasing, there's a stronger attraction for the electrons. So if you have a greater difference in electronegativity or a more electronegative bond, which could lead to a polar molecule, so the more polar the molecule is, the stronger the Coulombic attraction, which would mean that you're going to have a much stronger interaction between the molecules. So what does this actually mean? The greater the polarity is, the higher boiling points will be observed. Okay, so we would expect if we had a bigger difference in electronegativities, or if we had greater partial positive and partial negative charges on a molecule, that we would end up seeing higher boiling points. Notice that whenever we were talking about this initially with dipole-dipole interactions, I said for similar molecular weights or similar molar masses. Whenever we are comparing dispersion and dipole-dipole, and we say that dipole-dipole is a stronger interaction than dispersion, we're saying this for similar molecular weights, because at a certain point, you can have so many electrons and the molecule can be so large, or the protein can be so large, that then the dispersive forces will actually be stronger than the dipole-dipole interaction. So let's go ahead and look at a data table really quick. So in this data table, I've given a series of hydrogen compounds for second row elements. So we have CH4, so we have methane. We have ammonia. We have H2O. And we have HF. So, as we look at this, we know that CH4 is nonpolar. We know that ammonia is polar. We know that water is definitely polar. And HF is polar. So, if we look at the boiling points, we would say, well, water has the strongest intermolecular force. And methane has the weakest intermolecular force right here. But we just said that the greater the difference in electronegativity, the stronger the polarity would be, okay, or the more polar the molecule would be. So by that logic, because this has the greatest difference in electronegativity, we would expect that HF should have the strongest intermolecular force. Okay, so if we are basing this only off of the difference in electronegativities, we would think that HF would be the molecule that had the strongest intermolecular forces. If we're basing it off of molar mass, we would also think that HF would have the strongest intermolecular forces. But what we see is water has the strongest intermolecular forces. It's not surprising that methane, CH4, has the weakest intermolecular forces because it's nonpolar, it has the lowest molar mass and the least difference in electronegativity. But the big deal here is that it's nonpolar. All of these molecules, ammonia, water, and HF, are all polar molecules. So why is it that water, H2O, has a higher boiling point than HF? Well, it's actually a special type of dipole-dipole interaction, and it's called hydrogen bonding. So hydrogen bonding exists for molecules that have OH, FH, and NH bonds within it. What we'll see is these molecules actually have significantly higher boiling points than we would expect. Because what would happen is if you were to consider on this previous example, is we were to march down the periodic table from period to period, we would see that every time that we go down a period, so if we went from CH4 to SiH4 to GeH4, we would see that these boiling points would keep increasing on a graph. And this would make sense with dispersion, that as you're increasing the number of electrons in the molecular weight, the greater the polarizability and the stronger the intermolecular forces. But for NH3, H2O, and HF, their graphs would look more like this. We would see, like, if we had H2O here, then it would drop down to H2S, and then it keeps rising up. So it's really an exception for these three. And that's where hydrogen bonding comes into play. So what we'll see is there's something called conventional hydrogen bonding, and this is the only type of hydrogen bonding that we'll focus on in this class, is whenever you have an interaction between a bond that's OH, FH, or NH with a neighboring OH, actually just really an O, an F, or an N. And it could be any combination of these. So how do we remember which one's hydrogen bond? Well, hydrogen bonding, come to find out, is a lot of fun. Maybe after you've been studying this quite a bit, maybe you've had enough. So you're looking for FH, OH, and NH. Now, if you go on to take higher level biology courses or chemistry courses, you will start to encounter unconventional hydrogen bonding, where we have carbon, chlorine, sulfur, things like that. We're just going to completely ignore that for this class. So, but for instance, if you have something that looks like this, if you have HF, and then you had a neighboring NH3 or something like that, we would actually see a hydrogen bond being formed. It's a special type of Coulombic attraction between this lone pair, which we might call an electron donor, and then this H over here. So let's go ahead and look at a few more examples of these. So for hydrogen bonding, again, it's a special type of dipole-dipole interaction. It's just unusually strong. So whenever the dipoles get close enough, and then we can actually start to consider Coulombic attraction between that lone pair, like I specified on the previous slide, and that hydrogen. So for instance, down here I have a schematic of the cyclic HF hexamer. So notice these solid lines right here. These denote a covalent bond between hydrogen and fluorine. So what we'll see is that this has 6, hence the hexamer, HF molecules, but then there are hydrogen bonds denoted by the dashed lines, and we end up getting this stable complex. And some molecules form dimers, some form hexamers. It really depends on the bond angles, because it tries to limit the strain on the molecule. So you aren't going to see super acute angles being formed, because that's a lot of strain, and it starts to really affect the molecular geometry. So let's go ahead and try to figure out, why was H2O have such a higher boiling point than HF? Well, here's the reason why. If we were to consider water, we know that water has 2 lone pairs and 2 hydrogens. And if you think about that hexamer on the previous slide with HF, each HF molecule was only interacting, so for instance, if we were to consider this one, each HF molecule was only interacting with another 2 HF molecules. But for water can interact with more than just 1 or 2 other water molecules. So for instance here, what I've shown you is, here's a water molecule. This is donating this hydrogen. There's a hydrogen bond. There's interaction between the hydrogen and the lone pair. Water's special because it has that nice tetrahedral arrangement, and then it has that bent geometry. It's not linear. It's not trigonal pyramidal. It's bent because of that molecular geometry, and then also that difference in the electronegativity. Water can actually hydrogen bond with up to 4 other water molecules. So then, if you were to look at this centralmost water molecule, it can hydrogen bond with 4 other water molecules. And then as we move out, so here's a lone pair on this water, here's another lone pair. Well, in theory, this water molecule could hydrogen bond to another 3 water molecules. So you can see how water can form this really strong, complex system. So hydrogen bonds are super special. They're these special types of interactions that really play a major role in biological chemistry and just in chemistry in general. So we'll talk about that in just a second. The first thing I want to show you is there are different types of hydrogen bonding. There's intermolecular and intramolecular. Intermolecular is what we're going to focus on in this class. This is wherever you look for FH, OH, NH, and then interacting with either an F, an O, or an N. That would be looking at intermolecular hydrogen bonding. It's between molecules. Another part that we will not focus on is intramolecular hydrogen bonding. So interstates travel between states. So intra means within. So you could actually have hydrogen bonding within a molecule, and that could lead to a greater stability. So for instance, here, this molecule might be able to hydrogen bond with itself. This one, now this distance is too great, so it will not be able to have intramolecular hydrogen bonding. All of these molecules would be able to have intermolecular hydrogen bonding because they all have OH groups on them. But not all of them can have intramolecular hydrogen bonding. So to wrap up hydrogen bonding, what we want to say is, again, hydrogen bonding is found everywhere. It's in proteins and DNA. Hydrogen bonding is special because it's a strong enough interaction that it keeps molecule structure, but it's weak enough that it can still go in and things can be done. So for DNA, that double helix being zipped up and unzipped, that's because of hydrogen bonding. If it was a covalent bond, there's no way that we'd be able to go through and replicate DNA. If it was only dispersion, it may never actually get the base pairs to line up correctly. So hydrogen bonding is just that perfect balance of strength and then also being flexible and being able to be broken apart. Hydrogen bonding also plays a part in the transport of water in trees. It kind of works as a straw. As the water works its way from the xylem from the roots to the leaves to the tops of the trees, the water molecules just keep pulling each other up from the ground using this chain of hydrogen bonding. All right, so the very last intermolecular force that we're going to cover in this class are for ion dipole forces. And this is an attraction between an ion and a polar molecule. So for instance, let's consider sodium chloride and water. So we know that salt dissolves in water. So this would break up into the sodium ions and chloride ions. So how would water interact with these ions? Well, let's consider the distribution of the electrons within water. So we know that in water, oxygen is more electronegative than hydrogen. So there's a shift of electron density towards the oxygen. So the oxygen has a partial negative charge, and the hydrogens have a partial positive charge. In fact, I'm going to go ahead and put a 2 here because we're going to say that this partial negative charge is twice as large as each of those partial positive charges. So think about this. If you have sodium chloride, so you have your sodium's your cation, chloride's your anion. If sodium loses an electron, well, water could actually orient itself like this around sodium, and we'd have a Coulombic attraction between that partial negative charge on the oxygen and that positive charge on the sodium. Whereas for our anion chloride, chloride has a negative charge, so it could interact with the partial positive charge on the hydrogens of the water molecules. So we'll actually see ion dipole forces. So ion means you have an ion, and then dipole means you have a polar molecule. So how do we know when things will actually interact with each other? How do we know that salt dissolves in water, but salt doesn't dissolve in oil? How do we know that ethanol dissolves in water, but then sugar dissolves in water, but sugar doesn't dissolve in oil? Well, you may have heard of this saying, like dissolves like. So polar molecules will dissolve other polar molecules or ions, whereas nonpolar will dissolve nonpolar molecules. So this would be why you can mix oil and gasoline, but you can't mix oil with water. So again, that's a gross generalization. You can make an emulsion, but in general, they're not going to readily dissolve in each other. So like dissolves like. So you have to figure out whether your molecule is polar or not. And if it's polar, then it will dissolve in other polar solutions. Or if you have an ion, it will dissolve in polar, but it will not dissolve in nonpolar. So next time what we'll do is we'll summarize all of the interactions and try to come up with a good few general rules. And then we'll start to move on to additional properties.